There will be countless situations where we'll want to be able to calculate the probability under the normal curve. There are a few well-known cutoff values that you'll very likely come to know. We can also figure out any probability by using statistical distribution tables like those found in the back of your book. We know that many things in the natural world have distributions that approximate normality. Further, we know, thanks to the central limit theorem, that estimates of the mean have normal sampling distributions. This will extend to many of the statistical quantities that we estimate. If something follows a normal distribution, or approximately so, then we can use what we know about normal distributions to calculate probabilities within particular ranges. We'll work through an example below. First, however, let's look at the commonly known cutoff values. 50% of the normal distribution falls below the mean and 50% above. We know this because the distribution is symmetric. Roughly 68% of the values under the normal distribution fall within one standard deviation of the mean. Roughly 95% of values fall within two standard deviations of the mean. And roughly 99.75% of values fall within three standard deviations of the mean. So under the standard normal distribution, there are relatively few observations that fall outside the range, plus or minus 3. Oftentimes we'll want to know the probability of being less than some value on the normal distribution, particularly in situations where the insights from the previous slide will prove unhelpful. A standard score tells us how many standard deviations a value is above or below the mean. This doesn't have to be an integer value. For example, something could be 2.5 standard deviations above the mean. In the population, we would calculate a standard score by subtracting from the value the population mean and dividing by the population standard deviation. In the sample, we replace the population quantities with their sample analogs, the sample mean and the sample standard deviation. A standard score, or z-score, or perhaps I should say z-score, of -2 means that the observation is 2 standard deviations below the mean. The book talks about an example using the body mass index. Here, the mean for women is 26.08 and its standard deviation is 5.88, and for men the mean is 27.13 with a standard deviation of 4.88. Let's think about some probabilities that we could calculate. What if we wanted to know the proportion of women we would expect to have BMIs between 20 and 30? We'd first have to create z-scores for the values 20 and 30 separately. The z-score for 20 is -1.034, and the z-score for 30 is 0.667. So 20 is just over 1 standard deviation below the mean, and 30 is about 2/3 of a standard deviation above the mean. We could use the computer to help us figure out the two probabilities. The output here is from R, which, as I've said before, we'll learn when we get together in September. What this tells us is about 15% of the observations in the normal distribution are below -1.034, and almost 75% of them are below 0.667. If we subtract 0.15 from 0.75, that gives us the probability of being in the range 0 to 20, which is about 0.6. We could also display this visually. You can see the area under the normal curve up to 0.667 is colored in both red and blue, and that's about 75% of the distribution. If we look at the probability of being less than -1.034, that's just the red area. Isolating the blue area by subtracting the red from the red and blue area gives us the probability of being in the particular range we're interested in. We could also use probability tables from the back of the book. They start on page 247. I've recreated those tables here. Note that there are no negative values, but the normal distribution is symmetric, so the probability to the right of 1.03 is the same as the probability to the left of minus 1.03. Looking at the table, we see the probability to the right of 0.67 is 0.2514. That means the probability to the left of 0.67 is 1 minus 0.2514, or 0.7486, approximately 0.75. We know this because the area under the probability curve has to sum to 1. Looking at the value 1.03, we see the probability to the right of that is 0.1515, or approximately 0.15. That means the probability to the left of minus 1.03 is also roughly 0.15. Again, by subtracting 0.15 from 0.75, we get 0.6 just like above. Whenever we're working with data, you need to make sure that your results pass the smell test. That is, you want to make sure they have some face validity, that they are not wildly out of whack with your well-founded expectations. First, we know that 68% of the observations are within plus or minus 1 standard deviation of the mean. Since we got a smaller range than that, we would expect the probability to be smaller, and it is.